Hello, here we go. All right, so last time we went through a derivation, a derivative that gave us the slope of this line here and that's dz dp. Oh, my pen is so fat. Let me fix that. I swear that thing changes by itself sometimes. There we go. Okay, and we have dz dp that we derived last time. That was that implicit differentiation that gave us the slope is equal to minus p b squared over z a squared. Right? So we have that for the slope of our tangent line to the ellipsoid. We also kind of labeled our diagram here, and P is here, where P is the radius of a parallel of latitude on the ellipsoid. And that latitude, we said, that's the geodetic latitude, which lives right there. Phi is geodetic latitude. And let's see, Z, we said. Z is the geocentric coordinate, or the Earth-centered, Earth-fixed, XYZ, it's the Z coordinate. And let's see, we had N, which is that green line. N is radius of curvature. And it's called this. I hate this name. I think it's really misleading. Because it's not a radius of curvature at all, but it's called the radius of curvature in the prime vertical. I think it should be called the prime vertical in the direction of the radius of curvature, but that's just me. Okay, so N is the radius of curvature in the prime vertical. What else do we need to have here? So we have phi, we have our A, which is the length of our semi-major axis, our B, which is the length of our semi-minor axis. So I'm just going to put A and B are lengths of semi-major and semi-minor respectively. So let's label a few more of our angles on our diagram, and let's just do that using basic principles of right triangles. Remember, we have a lot of right triangles here. So I'm going to zoom in because it's going to be easier to depict these things. So on our diagram, we have our phi there, and I'm also going to label the fact that obviously if we have our phi angle there, this angle would be 90 minus phi. Remembering that this is a right angle and this is a right angle, we get this obviously is phi, and this is 90 minus phi. We just get all that from, comparing right triangles. If we took now this, consider this triangle here. And let's say we created from it an infinitely small triangle. So let's say we create an infinitely small triangle. Infinitely small, just like we do in baby calculus, triangle. Then this becomes still 90 minus phi. And this then is our dz, and this is our dp on the base. So from that we get the tangent, so we can say dz dp, and I'll go the other way, it'd make more sense. We would have the tangent of 90 minus phi equals opposite over adjacent. Oh, that's dz dp also. And that's going to be an important relationship for us. So if I were to zoom back out, that was just so we could get that, that dz dp in terms of the latitude. So what that leaves us with, get back to 100% here. So that gives us dz dp equals minus p over z. I'm going to just separate this out a little bit, times, where are we here? B squared over a squared. That comes directly from that differential that derivation we did. All I did was separate the b squared over a squared. And that equals the tangent of 90 minus the latitude, phi. So put that in your notes, have it off to the side that you can refer to, because we're going to be playing with that a bit. Now our goal here is to derive the radius of curvature, the radius of the parallel of latitude. And this is the only derivation I'm going to do on these ellipsoidal formulae, because you'll see why. They're pretty involved, and we'll be doing a lot of substitution and playing around with moving terms and that kind of thing. So the next thing that's helpful to note, since we can get it, turns out to be very helpful. I'm not going to move the diagram completely out, but it would be nice to know the slope of this line. Well, if you remember from basic geometry that the slope of any line that's perpendicular to another line is the inverse of the opposite of that slope. So that is the slope at n, the slope of n, or our prime vertical, is equal to minus dp over dz. So it's just the opposite of the inverse of the slope of the original line, right? Now looking back at our little infinite triangle there, what is minus dp dz? Well, that's just tan phi. So if we take this and we solve it in terms of dz dp instead of dp dz, we just invert and multiply by the opposite. We get dz, this leads us to dz dp equals the opposite of 1 over tan phi. That just follows directly from this relationship here. I just multiplied both sides by -1 and then flipped both of them. Okay, totally valid. So there's another value that we can use. So put that with the other one and have it handy. Okay, so remember that we need to use the defining characteristics of our ellipsoid. That is the flattening, eccentricity, which are made up of our A and our B, our lengths of our semi-major and semi-minor axes. So let's take that from there. So keep those equations we just worked with handy, and recall that the second eccentricity squared equals a squared minus b squared over a squared, right? And if I just play with that, oh yeah, and that equals, remember we said that's the same as 1 over b, or 1 minus b squared over a squared. Well, let's take this and this part and solve for b squared over a squared. We get b squared over a squared equals, where am I? 1 minus the eccentricity squared. Just basic baby algebra. Okay. And put that off to the side and have it handy because we're going to use that too. I think we have all the components we need in order to do this derivation. So from, I don't want to write in red. That's aggressive. So come on, give me a color. From all of this, or all of these, we have dz dp equals minus p over z times b squared, don't want to get my a's and b's mixed up, b squared over a squared, which equals minus p over z times 1 minus epsilon squared, right? I just replaced b squared over a squared here with 1 minus epsilon squared. And that equals, from our study of the picture, minus 1 over tan phi. All that is equal to dz dp. Okay. Phew. Just substitutions in algebra, but there's a lot of it, right? A lot of room for making mistakes. So make sure you're taking notes while I'm trying to be really careful. Chances are I'm going to make an error. I'm going to try and catch them as I go, as I have been, but this is correct here. And we can see how we got there. Now, if at any point during this video your eyes kind of fog over, your mind starts wandering, you have no idea what I'm doing, just pause it and work through these calculations yourself. They're really, everything I've done so far is just really straightforward algebra. No calculus, really. Remember, we're trying to get this by itself, p, or the radius of parallel of latitude. Okay, let's see, scoot up. Now we're going to do something a little weird. We're going to solve for using this. From there, we're going to solve for z over p. Well, why are we doing that? Well, you're going to find out. So if we just rearrange those terms, we get z over p equals I don't want to go to z over p equals yet. I'm going to do a couple steps before. So from our relationship here, we're going to take the next step and we're going to say z over p times 1 over 1 minus epsilon squared equals tan phi, just algebra steps, and that yields what we want, which is z over p equals 1 minus epsilon squared tan phi. Okay, cool. Now we're going to use that. And scoot up, get some more writing room here. All right. So now we're going to do another little trick. We're going to square both sides. Well, why are you doing that, Rob? Well, we're going to find out. That gives us z squared over p squared equals 1 minus epsilon squared, all of that squared, tan squared phi. Just squared both sides. Should use my parentheses, right? And then we get z squared equals p squared times 1 minus epsilon squared squared times tan squared of phi. Okay, so now we have something else to work with. Whenever we work to solve these terms, you can bet we're going to substitute somewhere coming up, right? Scoot that up. I'm going to keep that handy. And we're going to come up with another representation of z squared. And this is going to come from the definition of our ellipse. So recall, for our ellipse, the definition is p squared over b squared plus z squared over a squared equals 1, right? Well, let's solve that for z squared. And we get z squared equals a squared minus p squared times b squared over a squared. That's just solving for z squared from our ellipse definition. Now recall from above, I'm going to say recall also that b squared over a squared is equal to 1 minus epsilon squared. And we derived that earlier, so we're going to use that relationship. We'll plug that into here to get z squared equals a squared minus p squared times 1 minus epsilon squared. There we go. Okay, we're getting there. And we're going to use that. So now if we take that relationship and we're going to plug it into that for z squared. we end up with a squared minus p squared. Let me go the right direction here. Oh, I was. Okay. I'm using the wrong color, that's why. So, a squared minus p squared from just directly above it times 1 minus epsilon squared equals p squared from up there on top times 1 minus epsilon squared times tan squared phi. Whew. We're getting closer. We're getting closer. And if we rearrange terms a little bit there, let me move it up. There we go. And we notice that we have a 1 minus epsilon squared on both sides, so we can clean that up just a little bit. That goes away, and that becomes a non-squared term. I just divided both sides by the 1 minus epsilon squared, and that gives me a squared minus p squared equals p squared times 1 minus epsilon squared tan squared of phi. I put a theta up there, I meant phi. Too many symbols. All right. Okay, so now solve for p squared. We get p squared equals a squared minus p squared over 1 minus epsilon squared tan squared phi. Use my parentheses. There we go. Good notation. It's important. And scoot it up some more. I wish I had a bigger space to write in. That's all right. And if I take that one step further, if I just use the definition of the tangent, then I get p squared equals a squared minus p squared times the cosine squared of phi. Again, just the definition of a tangent over 1 minus epsilon squared times sine squared phi. And I'm just going to make a long story short here. I can go through a bunch more solving, but it's just solving with algebra. I'm not going to do that. But what you end up with is p equals a cos phi over 1 minus epsilon squared. Whoop, I don't want to close that yet. Make sure I get all my components. 1 minus epsilon squared sine squared phi. All of this to the 1/2. And that's what we want. So we have solved for the radius of a parallel of latitude. The rest of them I'm going to just throw at you. You're just going to have to believe me because I'm not going to derive anymore. There's a lot to that. And I definitely, I didn't skip steps. Well, I kind of did at the very end, but I did rush through pretty quickly. So make sure you go through that. You understand that derivation. So I can say similar. Whoop. derivation yields the length of our radius of curvature in the prime vertical n, which was that green line, is equal to a over 1 minus epsilon squared sine squared phi to the 1/2. And something there should look very familiar. Look at our p-value. Let me just circle a part of it. Look at this part here. The a over, forget about the cos phi, look at the rest of it. Isn't that identical to n? So that p becomes n cos phi. Much prettier, much nicer than the mess above, right? And that just leaves us with our z, and I'll just write it down. And our z value, or that Cartesian coordinate, the geocentric Cartesian coordinate, z is equal to n, I'm not deriving this, times 1 minus epsilon squared sine phi. So these are the formulae you should keep in your notes. They will be very handy. And at some point you might be asked to derive another one of those. Cool. So we have the length of our radius in the prime vertical. We have our radius of a parallel of latitude on the ellipsoid, and we have our z component, or our z Cartesian coordinate. And if I just go back to that diagram, let me do that. What do we have? So the parallel of latitude's given, right? So we have a parallel of latitude. That's what we're interested, that's what we use to get our interested components. We have our parallel of the latitude, we have our length of the radius of curvature in the prime vertical, and we have our z. So we have everything, and a, remember, is defined by our ellipsoid, and b is defined by our ellipsoid. So we have just derived, well, we derived one of the components, and then just I threw the other ones at you. But with those formulae, we can do just about anything with information on the ellipsoid. Okay, so that was super fun. Change topics a little bit. Now we'll talk about the radius of curvature. And you'll see why I'm in opposition to the term radius of curvature in the prime vertical. It implies that n is a radius of curvature, and in fact it's not. So let's talk about radii of curvature. Now the length of a radius of curvature can be a little counterintuitive, right? So if we have a circle, let's say we have a circle and we have a radius. We know that that circle has a radius, and that radius is uniform, right? We'll call that r. Well, that's a defining characteristic of that circle. And if we just have a circular curve, so any subset of that circle, so if we just have a circular curve of radius r, That just means that every point on that curve has a radius r, right? Well, if I have another circle, and let's say the radius of that circle is 2r. Doesn't it make sense that this circle has a much tighter curve than this circle? So the bigger the circle, the more a subset of that circle approaches a straight line, right? So in fact, if we have a straight line, then, always gets light. If I have a straight line, then we say that the radius approaches infinity. As the radius of a curve, as a circle gets bigger and bigger, that is, the radius gets longer and longer. If we were to just focus on one part of that circle, it would start looking like a straight line. So if I have a very flat curve, let's say that's R1, that has a radius of R1. And if I have a much more round curve, I guess for lack of a better word, and we say that has a radius of R2, well, obviously R1 is greater than R2, right? R1 is flatter, so it's less curvy than R2. These are just concept image points to try and get past that counterintuitiveness of radius of curvature, where they are larger, where they are smaller. So if let me go back to my diagram. There's a reason why I'm going through this to such ad nauseum. I'm just going to erase all this other stuff. I don't need it. And if I were to take a look at a point on the semi-major axis and the surface of the ellipsoid, we'll call that point A, and a radius and a point on the semi-minor axis and the ellipsoid, we'll call that point B. Well, thinking about the curviness of a curve, the ellipse is flatter at point B than it is at point A, isn't it? The curve is more acute at point A than it is at point B. So the radius of curvature I'm just going to say RCB. The radius of curvature at B is greater than the radius of curvature at A. And the reason that's counterintuitive is because A, my semi-major axis, is greater than B. So I'll say but, and that's B. A is greater than B. That's what makes that pretty counterintuitive. So just remember that a radius of curvature the magnitude of a radius of curvature is dependent upon the curviness, for lack of a better word, or the dynamic of the curve for which it's a radius. Also important to note that every point within a quadrant, every point along, so if I'm just looking at quadrant 4 here, every point along the ellipse has a different radius of curvature, right? On a circle, it would be a uniform radius of curvature, and that would be the radius of a circle. But on an ellipse, that radius of curvature is changing. In fact, it's increasing. I'll just do this. The radius of curvature is increasing as we get closer to B. Okay, just concept image stuff, right? Okay, I'm just going to scoot this over to this side so I can write here. So let's see, a good note to make is that on an ellipse, the radius of curvature increases as we move, I'll say along the ellipsoid. So as we move along the surface of the ellipse from the semi-major axis and here we're calling it A, to the semi-minor axis. I know, handwriting. It increases that way. So, okay, what do we want to do here? Oh, I'll say further. Each of the points on that path, so just within a quadrant, has a unique radius of curvature, right? It continues to increase, so no 2 points within a quadrant can have the same radius of curvature. And the other observation, and this is very subtle, it is the length, so the radius of curvature is the length of the normal vector to the curve at that point. And I've been using RC just for help with that concept image. We tend to call, let me scoot this up. We tend to use capital M for radius of curvature, and that's what I'll use from now on instead of R sub C, because then I start getting too many R's. M for radius of curvature. Now, remember how I said I hate the term radius of curvature in the prime vertical? Well, here's why. Let me erase this stuff. Let me zoom into this quadrant here. And I'll use green. So remember, the distance here is n, or the radius of curvature in the prime vertical. M, the radius of curvature of the curve at this point, we'll call it Q, does not extend all the way to the axis. In fact, it's shorter. M. So now you can see why I don't like that term. To call n the radius of curvature in the prime vertical implies that it is a radius of curvature, which it is not. It is the prime vertical in the direction of the radius of curvature. M has a direction, and if we extend M to the semi-minor axis down there, that is n. So a semi-major, I'm going to do another diagram. Let's see. I'm going to pull in, take a second, pause it, and pull in a different image. Magic. So here's our semi-minor axis, here's our semi-major axis, and let's make the observation from above. It just plays off of what we said in our observations above. Let's see. In the meridian plane, remember, which is a plane going through the spin axis of the Earth, so if we're staying in the same line of longitude, basically is what this is saying, of an ellipsoid, comma, the radius of curvature M is minimum at the equator So here, the radius of curvature is at a minimum. And you can guess the next part, I'm sure, maximum at the pole. So here, and this is true also, obviously, on wherever that criteria is met. So this is maximum M for the quadrant. So here, phi, our latitude equals 0 degrees, and here our latitude equals 90 degrees. Cool, 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 cool. So let's see if I can draw this. Let's say I have a bunch of points along the surface of my ellipsoid. They don't have to be evenly spaced. The concept is still clear. I'm going to erase these so they don't get in the way. Well, the radius is minimum in the plane of the equator. So I'm going to try to keep my... So here's my M. Let's call this, let's see, what should I get? Q. So this is Q1, Q2. I'm just naming my points. Q3, Q4, Q5, Q6. So I'll call this M1. That's my radius at the equator, my radius of curvature for a point at the equator on the surface of the ellipsoid. And then if I have, I'm not going to draw this very well, Q1, so this would be, oh, it's supposed to go to, my notations, my subscripts are getting messed up. This should be M0. I'm calling this Q0. Let's call this Q0. So that's M0. This would be M1. And I could keep going. That gets longer. This is going to work out very well. M2, M3, and so on, so that eventually I end up with, this is really hard to draw a straight line. At Q6, I'm not going to draw Q4 and Q5 because my diagram is getting a little too convoluted. So at Q6, I have this radius of curvature, say, that goes down to here. And that would be M6. And what I have then is this curve between the endpoints of my, let me use a different color. I have a curve between the endpoints of my vectors, right? And it's a concave down curve. My my image is much better in my notes. It's hard to draw on that thing. But in our books, let me look up what figure it is. Well, looks like our book doesn't have an image of what I'm trying to do here, but the basic idea here is that M increases as the radius of curvature approaches the spin axis, right? And we have a formula for that. Just like we have a formula for M, we say M equals, so this is the radius of curvature on an ellipsoid, is equal to A. And it's going to look very familiar because all of these have sort of a similar flavor. A, 1 minus epsilon squared over 1 minus E squared, or epsilon squared. There, I did it again. I'm used to using E. NGS uses E. So 1 minus epsilon squared sine squared phi. And here's where it's a little different. All of that to the 3/2 instead of 1/2. So a little bit different than N. I'll just write N here just so you can compare. Let's see, what was that? That was A over 1 minus epsilon squared sine squared phi to the 1/2. So you can reduce, obviously, since we have this part here, we can separate the 3/2 into 1/2 times 2/2, and you could write M in terms of N if you wanted to, but it really, by the time you get done, it's not that helpful. Just remember that M has a couple of additional components. One is this 1 minus epsilon squared in the numerator, and the other is it's 3/2 instead of 1/2. Other than that, M and N are the same, and that makes sense since they're related, right? They're parallel, they terminate at the same point on the ellipsoid, they just have different starting places. Yeah, so radius of curvature, radii of curvature, important concept. So let's just, I'm gonna move this over and try not to get rid of it completely. Let's, just like we did before, let's talk about a couple observations. So observations. M and N are magnitudes, that is, lengths. So are always positive, or represented as positive. Remember, magnitudes don't have a direction. So if you go through all the math and you come up with a negative number, 1, check to make sure your math's right. If it is, and you just have a negative where you should have a positive, just take the absolute value. It's a magnitude. That's, that's part of the definition of a magnitude, is it's always positive. Let's see. That's one observation. 2, m does not equal n, as n extends because n extends to the minor axis always. And so n extends to the minor axis while m does not. I'm not going to write it, but while m does not, except in the case where it's along the spin axis of the Earth, then it's part of the minor axis itself. So, I mean, the whole thing is the minor axis. You can't really say it extends to the minor axis. But in general, I mean, in specific, except for the case where m is parallel to the spin axis, m does not equal n, and n extends to the minor axis. Let's see. M is the radius of curvature at a point while just trying to drive home the difference between these two types of radii because it can get confusing later. While n is the radius of curvature in the prime vertical and extends to the minor axis. Let's see, further, we can say m is less than or equal to n, and m is, I'll say, I'm going to finish that thought. M is less than or equal to n everywhere, and m equals n only at the pole. So m is equal to n at the pole and less than n everywhere, strictly less than n everywhere else. That might be a better way to write that. M equals n at the pole, m is strictly less than n everywhere else. Okay. Oh, here we go. This is a good one. Another good observation. Like, now, let's see. You know what? I'm not going to give you any more. That's enough observations on that. And one last point to make, so I'll scoot that up. Sort of a new idea, but it's definitely related to what we were doing. To clean things up, let's just quickly, before we wrap up, I'm going to make a circle. So if this is looking down on the ellipsoid, so here's the pole. And think about this really carefully. If we're looking straight down on the pole, all of the parallels of latitude and the equator itself are circles. They're not ellipses, right? We're looking down. The Earth is elongated all the way around the plane of the equator and shortened at the poles. So if we move our perspective so we're looking straight down on the pole, it looks just like a sphere would. That is a circle, right? And with that, I just want to make some comparisons between the ellipsoid and the circle. So if that's 2 lines of longitude, we have our delta lambda, which is interesting, isn't it? We've changed our notation for parallels of latitude, but we've kept the same notation for lines of longitude, and that's because they work the same way. So this is the pole. And if we have point A here and point B here, I just want to make some comparisons. And this latitude, this is our latitude phi on the ellipsoid, or psi on the sphere. Let's compare some of the formulae. So on the sphere, and I'll put ellipsoid over here. What we learned before is that the radius of a parallel, r sub p, is equal to the radius of the sphere, r, cos times the cosine of psi, right? And s, if this is s, that's the arc length between A and B, s equals r sub p, or the radius of the parallel, times delta lambda. Always working in radians, right? On the ellipsoid, let me scoot this over just a little bit. So on the ellipsoid, we would expect it to be very similar, wouldn't we, since we have a circle in both cases? Well, we do. So on the ellipsoid, we have P, which is what we call the radius of a parallel on the ellipsoid, equals n cos phi, which is our latitude, like psi, except on the ellipsoid, and s equals P times delta lambda. Super similar. So when it comes down to working in, from a top-down view, it simplifies quite a bit and is very familiar with our work on the sphere. So lots of math this time, lots of derivations, but it's important, I think, to see how the ellipsoid creates so much complexity over the sphere. And we need to be considerate of that when we're working in an engineering environment, because we need that level of precision. All right, I think we will stop there and call that one a day. If you have any questions, reach out. And yeah, that's it. Have a good day.